In order to study kinematics, we need some basic mathematical and geometrical notions related to the quantities which can describe the motion of the point-like bodies. These notions are the scalar and the vector. Those physical quantities, which are completely determined by a numeric value and a physical unit, can be described with scalars. Typical examples are the time measured between two events, let's say 10 seconds, and the volume of a body, let's say 100 cubic centimeters. But in kinematics we also need another type of quantity, called vector. We define the motion of a point-like body as its displacement or the change in its position. For a ball moving from a given position to another one, we can use the point mass model, where we identify the position of point mass with the center of the ball. When we talk about the motion of a body we have two things in mind. How much is the distance between the initial position O and the final position P of the moving body? And in which direction has the body moved, that is, what is the direction of the line connecting the initial position O and the final position P? Then the motion can be described with a directed straight segment. Its graphical representation is an arrow pointing from the initial position O to the final position P, and its notation is given by the letters OP with an arrow over them. We call this directed straight segment the displacement of the body. The length of the directed straight segment OP is equal to the distance between the starting and end points of the motion. And the direction of the segment gives the direction of the motion, that is the direction of the line connecting the points O and P. This segment is completely determined by the relative positions of the points O and P. As a result, the location of the starting point of a displacement is irrelevant. What matters is the relative positions of the starting and the end points. In the case of two or more displacements of a body, we can construct its net displacement. The composition of the displacements is based on the parallelogram law. If there are two different displacements with the starting point O and the end points P1 and P2, we can proceed as follows. First we construct the displacement starting the point P2, which is parallel with the displacement OP1. Let's denote this displacement with P2P, directed to the point P. Then we construct the displacement from P1, which is parallel with the displacement OP1. This displacement also ends at the point P and it is denoted with P1P. Now there are two ways to reach the point P from the point O with these displacement vectors. In the first way, we move along the displacement OP1. And then along the displacement P1P. Which is equivalent to the displacement OP. In the second way we take the route along the displacement OP2. And then along the displacement P2P, which also gives the net displacement OP. Then the parallelogram law states the following. The net displacement OP of the two displacements OP1 and OP2 is given by the diagonal OP of a parallelogram constructed from these displacements. Now we can define vectors as such directed straight segments or displacements, which can be constructed by using the parallelogram law. Here the displacement OP is a vector. Furthermore, we can find such displacements which can be used to construct the displacements OP1 and OP2 as well. This shows that OP1 and OP2 are also vectors, and we can conclude that any general spatial displacement is a vector. However, not every directed straight segment is a vector. For example, the rotation axes of spatial rotations are also represented with such segments, where the length and the direction of the segment indicate the rotation angle and the direction of the rotation axis. But the composition of such rotations is not commutative, that is, they don't obey the parallelogram law. Then the oriented rotation axes cannot be considered vectors. Just as a reminder, let us have a brief overview on the basic vector operations. First of all, we note that two vectors are equal if they have the same length and direction. That is, if we have the vectors A and B, then the arrows A and B with the same length and direction indicate that the two vectors are equal. The boldface type will be used as the vector notation throughout this lecture. Here we have an equation stating that vector A is equal to the vector B, which is a vector equation and combines two statements in one equation. The first statement is that the length of the vector A is equal to the length of the vector B. The length or the magnitude of a vector is simply denoted with the letter of the vector without using the boldface type, or it can also be denoted with double vertical bars, similar to the notation of the absolute value of a number. The second statement of the vector equation is that the vectors A and B have the same direction. That is, they are parallel and have the same orientation. This means if we have two vectors, let's say A and C, and if they have either different lengths or different directions, then they are not equal. Here we see that the vector C has the same length as the vector A, but it points into a different direction. Therefore, the vectors A and B are not equal. The first vector operation presented here is the sum of two vectors, which is called resultant, and is defined by the parallelogram law. If we have two vectors A and B, which point in different directions, we can just take the first vector and translate the tail of the vectors to the tail of the other one. Then we construct a parallelogram from the vectors. The diagonal vector of the parallelogram with the tail at the tails of the vectors A and B is the resultant, and denoted with A plus B. By the construction of the parallelogram, we can see that the sum of two vectors is commutative. That is, A plus B is equal to B plus A, meaning the order of the vectors does not matter in this operation. We can also see that the sum of vectors is also associative. If we take the vector A and the vector B, where we translate the tail of B to the head of A, and the vector C, by translating its tail to the head of the previous vector, then we can construct the vector A plus B and the vector B plus C. Now the resultant A plus B plus C can be constructed in two different ways. Either we take the sum of the vector A plus B and the vector C, or we take the sum of the vector A and the vector B plus C. Then we can write that the vector A plus B, plus the vector C is equal to the vector A plus the vector B plus C, which shows the sum of vectors is associative. If to denote the angle between the vectors A and B with alpha in the parallelogram, we can write that the angle at the head of the vector A is equal to pi minus alpha. Then we can determine the length of the resultant A plus B by using the cosine theorem, which gives a squared plus B squared, minus 2ab times cosine pi minus alpha. By virtue of the trigonometric identity for the addition of angles in the argument of the cosine function, the last term in the expression reduces to 2ab times cosine alpha. If we know the lengths of the vectors A and B, and the angle between A and the resultant A plus B, then we can compute the length of their resultant. Now, if beta is the angle between the vector A and the resultant A plus B, then we can use the sine theorem to determine the direction of the resultant, since the sine of the angle beta is equal to the ratio of the length of the vector B to the length of the resultant A plus B, multiplied by the sine of the angle alpha. Let us continue with some further basic vector operations. Based on the sum of two vectors, we can introduce the negative of a vector, which is also a vector with the same length, pointing into the opposite direction. Here we can see the opposite of the vector A, which is denoted with minus A. In the vector equation we can see that the sum of these two vectors is equal to the zero vector, where the zero vector has zero length and an arbitrary direction. The vector equation also shows that the lengths of the vector A and minus A are equal. They are also parallel but they have opposite orientations. Then we can define the subtraction of two vectors, as the sum of the first vector and the negative of the second one. If we have the vectors A and B, then we take the opposite of B, which is minus B, and translate it to the head of the vector A. Now we can take the sum of the vectors A and minus B, where we denote the resultant with A minus B. We see that in the vector equation the vector A minus B is defined by the sum of A and minus B. The next operation is the multiplication of a vector with a scalar. For a vector A, we can give any real number, denoted with C, for which we define the multiplication of the vector A with the scalar C, or C times A, as a vector pointing to the direction of A but with the length equal to the magnitude of C times the length of A. By using this operation, we can also define the unit vector which is unit length. For a vector A, the unit vector EA is defined as the multiplication of A with the inverse of its length. Then the length of unit vector EA is equal to 1, and it points into the direction of the vector A, as we see in the figure. When we use vectors in mechanics, we also need to know how to decompose vectors in terms of other vectors. We already mentioned that a vector can be constructed by using a set of other vectors, that is, it can be the resultant of the sum of other vectors. For example, let's take the vector A, which can be constructed from the vector B, translated its tail to the one of the vector A, and the vector C, which points from the head of the vector B to the head of the vector A. Then the vector sum of B and C gives the vector A, and we can say the vector A is decomposed to the vectors B and C. But we can have many other ways to make such decomposition. For example, we can take the vector D, the vector E, and the vector F. Their vector sum also gives the vector A. What we use generally for the decomposition is a set of coordinate basis vectors. If we consider the rectilinear or Cartesian coordinate system, with the axes x, y and z, we can define the basis vectors ex, ey and ez of the coordinate system. These vectors are unit vectors, that is, they have unit length. They are also mutually perpendicular to each other, as we can see in the figure. Now, if we consider the vector A with the tail at the origin and the head at the point P, we can determine the angle alpha between the vector A and the basis vector Ex. Similarly, we can specify the angle beta between the vector A and the basis vector Ey, and the angle gamma between the vector A and the basis vector Ez. We can also project the distance of point P, or the length of the vector A, onto the coordinate planes and axes. These projected distances can be calculated from the length of the vector A and the angles defined here. And they are called as the components of the vector in the Cartesian coordinate system. The projection of the length of A onto the x-axis is denoted with Ax, and it is equal to A times cosine alpha. It is called the components of the vector A in the direction of the x-axis. The components of the vector A in the direction of the y-axis is denoted with Ay, and it is equal to A times cosine beta. The third component Az is in the direction of the z-axis, and it is equal to A times cosine gamma. The cosines of the angles alpha, beta, and gamma are called directional cosines, since they determine the direction of the point P with respect to the axes of the coordinate system. Then the decomposition of the vector A with respect to the coordinate basis vectors Ex, Ey and Ez is the linear combination Ax times Ex, plus Ay times Ey, plus Az times Ez. Since the coordinate basis vectors are fixed, the vector A is completely determined by the coordinates Ax, Ay and Az. This linear combination is called as the basis expansion of the vector A, or we say that the vector is expanded in the basis Ex, Ey and Ez. The length of the vector A can also be determined in the terms of its coordinate base expansion. If we denote the projection of its length onto the xy-plane with h, then we can use the Pythagorean theorem and write that the square of the length of the vector A is equal to h squared plus the square of Aaz. If we apply the Pythagorean theorem again, we can write h squared as the sum of ax squared and ay squared. Then a squared is the sum of the squares of ax, ay and az. That is, the length of the vector A is the square root of the squared sum of its components in the Cartesian coordinate system. As a result of the basis expansion, any vector equation is equivalent to three scalar equations. That is, if the vector A is equal to the vector B, it means we have three component equations, namely, ax is equal to bx, ay is equal to by, and az is equal to bz. Then we can work with the scalar equations by determining the components, as the expansion of the vector equations in the given coordinate basis. The last two vector operations which we use in kinematics are the scalar product and the cross product of vectors. Let us start with the scalar product. For the vectors A and B, we can translate the vector B to the tail of the vector A and determine the angle phi between them. We denote the scalar or dot product of the vectors A and B with A dot B, and define it as the multiplication of the magnitudes of I and B with cosine phi. If we denote the projection of the vector A onto the vector B with AB, then AB is equal to A times cosine phi. Now, we can also write the dot product of the vectors A and B as AB times the length of B. As a consequence of the definition of the dot product of the vector A with itself is equal to the square of the length of the vector A. Then we can say that the length of a vector is the square root of its dot product with itself. If we exchange the vectors A and B, then the dot product of the vector B and the vector A will be equal to B times A times cosine 2 pi minus phi, as we measure the angle from the vector B now. But this result is equal to AB times cosine phi, that is, the dot product is commutative, which means that A times B is equal to B times A. We also see from the definition, if the length of the vector A or B is 0 or A is perpendicular to B, then the dot product of A and B vanishes. Since the basis vectors of the Cartesian coordinate system are mutually perpendicular to each other, their scalar products with each other vanish. The dot products of the basis vectors with themselves give unity, since each of them is a unit vector. These properties of the coordinate basis are very useful, if we expand the vectors A and B with respect to the basis vectors in the scalar product. We can also show that the scalar product is distributive, and we can take the dot product for each term in the parentheses. The terms with the dot products of different basis vector vanish, while in the terms with the dot products of the same basis vector, the dot product gives 1. As a result, the scalar product of the vectors A and B will be equal to Ax times Bx, plus Ay times By, plus Az times Bz. The last vector operation we consider here is the vector or cross product. We can use the vectors a and b again with the angle phi between them. The vector product of the vectors a and b is defined as a vector, denoted with a cross b, which is perpendicular to both a and b. The vectors a, b and the vector a cross b forms a triplet with the right-hand rule. The length of the vector product of a and b is defined as the length of a times the length of b times sine phi. It follows from the definition applying the right-hand rule that the cross product is anti-commutative, that is, a cross b is equal to minus b cross a. It also follows from the definition, if the length of a or the length of b vanishes or the vectors a and b are parallel, then their cross product vanishes. The cross product of any two different coordinate basis vectors always gives the third one, with the permutations ex, ey and ez in the cross product. The cross products of the coordinate basis vectors with themselves vanish, since the vectors are parallel with themselves. We can use these relations in the basis expansions of the cross product, which gives the product with the x components equal to ay times bz minus az times by. With the y component equal to az times bx minus ax times bz. And with the z component equal to ax times by minus ay times bx.